Hello dear student, welcome back to the second lecture in molecular spectra, and we will be continuing our discussion on Raman spectroscopy in this lecture also. Previously, we have discussed about the Raman effect. We have discussed about Raman spectra, that is the characteristic lines that we see in Raman spectra, the Rayleigh lines, the stroke lines and the anti-stroke lines. And we tried to explain the Raman effect using the classical theory. We have also seen that while explaining using classical theory, we couldn't explain why the stroke lines are highly intense than the anti-stroke lines. And in this video, we will try to make up with this failure. In this video, we will be talking about the quantum theory of Raman effect. And using quantum theory of Raman effect, we will explain the vibrational Raman spectra, the rotational Raman spectra. Then we will see how this Raman spectroscopy or the Raman effect is used to determine the structure of diatomic and polyatomic molecules. Towards the end, we will see how a Raman spectrometer will work, what are its components. So welcome to the lecture. In the classical theory explanation, the failure was we were looking into the bulk structure. We were looking into the atom, we were looking into the molecules. But we know that indeed every atom, every molecule is made up of energy levels. They have specific energy levels. And in Raman spectroscopy, what we know so far is a radiation is interacting with a matter. And we know that when a radiation interacts with an electron in the ground state, this electron absorbs that radiation and goes into a higher state. And after some time, it will decay itself into a lower state and emits another radiation. So we can use this principle to explain the Raman effect. In the Raman effect, what we have is a radiation interacting with matter, and the matter scattering radiations in three different frequencies or more different frequencies: the Rayleigh lines, the stroke lines and the anti-stroke lines. So consider an electron which is in the lowest energy state E1, and this is excited to another virtual level. Here I say virtual level because it is easy to say that it is not a stationary level, because we want these to decay as fast as possible. Therefore, it is being excited to a virtual level. We know that every electronic state is composed of different levels of a vibrational energy state. Every electronic state is composed of different vibrational energy state, and every vibrational energy state in turn is composed of different rotational energy state. So the electron which is being excited to the virtual level have to decay to the energy level E1, but it can decay to any of these vibrational or rotational energy levels of the energy level E1. It can decay to the same vibrational or rotational energy level as the same, and this will give you the Rayleigh scattering. It can decay to a higher vibrational level of the same electronic state, and it will emit a radiation of a lower frequency, giving you the stroke lines. Or it can either decay to a vibrational energy state lower than the initial energy state, emitting radiation of a higher frequency, and this will give you the anti-stroke lines. So if the incident radiation had an energy of h nu 0, during the Rayleigh line, the electron absorbed the energy h nu 0 and also emitted the energy h nu 0, giving the difference between the energies to be equal to 0. While in the case of stroke lines, it absorbed h nu 0, it released only h nu, giving an h delta nu, where delta nu here is positive. In the case of the anti-stroke lines, it emitted H nu 0 and also it absorbed H nu 0 and it emitted H nu, and this nu is added, it is positive, and we will have an energy difference of H nu. In the case of stroke lines, it had an energy emission of nu v, and here an energy of nu v is added to this initial energy state. And we can see that using simple logic, it is possible that the electron will emit an energy which is less than the absorbed energy, and this is in the case of the stroke lines. It can either emit energy which is same as the absorbed energy, or it is possible that the electron can emit energy which is slightly lesser than the absorbed energy. But it's highly unlikely that the absorbed energy is lesser than the emitted energy. That is, the emitted energy being higher than the absorbed is highly unlikely, and this is the case of anti-stroke lines. Therefore, the Rayleigh lines are highly intense because the emitted and the absorbed are same. The stroke lines are intense and because the probability that the electron will absorb a higher energy and release a lower energy is much probable. Therefore, the stroke lines are intense, but the electron being absorbing a higher energy, and releasing a higher energy is unlikely and less probable. Therefore, the anti-stroke lines must be less intense. And this actually explains why the anti-stroke lines are less intense than the stroke lines. Also, while referring to Raman effect, we have seen that the Raman effect is specific, or the scattered light, the scattered intensities are specific to the substance with which the radiation interacts. And we also know that the energy levels are the characteristic of the substance. Therefore, this theory successfully explains why the Raman effect is characteristic for each substance, that each substance gives separate Raman effect and Raman scattering spectrum, and this is because the energy levels of every substance is different and it is a characteristic of each substance. Now, we can use this quantum theory. Since quantum theory has successfully explained the Raman effect, we can use the same quantum theory to explain the hyperfine structures. The hyperfine structures, we have seen that we have a rotational hyperfine structure and the vibrational structure. So we'll look into the hyperfine structures and try to explain these using the quantum theory. So, vibrational Raman spectra arises due to transition of molecules from one vibrational state to the another vibrational state inside the same electronic state. We already know that an electronic state is composed of different vibrational energy state, and the electronic energy state itself is V is equal to 0, and we have different vibrational energy state here. Therefore, when transition occurs in between these energy states, it will give you the vibrational Raman spectra. The selection rule for getting vibrational Raman spectra is delta V is equal to 1. That is, transition can be made between adjacent energy levels. At ordinary temperatures, these molecules will be at its lowest vibrational energy state, that is V is equal to 0. Therefore, the only transition possible with the selection rule is from 0 to 1, and this is the prominent transition. For some molecules, the energy state will be V is equal to 1. Therefore, the transition possible, the adjacent energy levels to V is equal to 1 is V is equal to 0 and V is equal to 2. Therefore, The transition from V is equal to 1 to V is equal to 2 will give you the stroke lines, and the transition from V is equal to 1 to that to 0 will give you the anti-stroke lines. The vibrational energy of a diatomic molecule can be found from the enharmonic oscillator, and you have already seen this while learning the vibrational energy levels. So similarly, we can consider a molecule as an enharmonic oscillator and find its vibrational energy levels, and the vibrational energies are given by E is equal to V plus half nu E bar, where nu E bar is the wave number, minus V plus half a square x E nu E bar. And the prominent transition, as we have seen, is V is equal to 0 to V is equal to 1. So for V is equal to 0, the energy E will be, for V is equal to 0, it will be half nu E bar minus 1 by 4 Xe nu E bar, and this is for V is equal to 0. For energy V is equal to 1 will be equal to 3 by 2 nu E bar minus 9 by 4. What we have here is 3 by 2, the square will be 9 by 4 Xe nu E bar. The difference between these two energy levels, the delta E, is the difference between, here we have 1. So the difference between epsilon V is equal to 1 minus V is equal to 0 will be equal to 1 nu E bar minus, what we have here is 9 by 4 minus 1 by 4 will give you 8 by 4, that is 2 Xe nu E bar, which is equal to 1 minus 2 Xe nu E bar. Therefore, the difference, the energy difference of the transition from 0 to 1 is nu E bar 1 minus 2 Xe. That is, the frequency which we will get in the Raman spectrum will be nu 0 plus or minus this energy difference, and this nu 0 stands for the Rayleigh lines, and the plus nu E bar stands for the stroke lines, and the minus nu E bar, minus delta E, whatever, will give you the anti-stroke lines. And using quantum theory, we have successfully explained the vibrational Raman spectra. Now let us see the rotational Raman spectra using the quantum theory. The rotational Raman spectra arises due to transition between the adjacent rotational levels of the same vibrational state. We know that every electronic state is composed of its vibrational states, different vibrational state, and every vibrational state in turn is composed of its own rotational energy state. So if the transition is happening between the adjacent rotational energy states of the same vibrational state, then we will get the rotational Raman spectra. The selection rule for this transition is delta J is equal to 0, that is, transition is happening in the same energy level, or it is plus 2 or minus 2, that is, it is happening in the second adjacent level, higher or the lower. If it is happening in the same energy state, we will get the Rayleigh lines. If it is happening to a higher energy state, delta J is equal to 2, then we will get the stroke lines. And if delta J is equal to minus 2, then we will get an anti-stroke line. And as you have already learned, the rotational energy of a diatomic molecule can be derived as energy is equal to Bj into J plus 1, where J gives you the rotational energy state and B is a constant given by h divided by 8 pi IC, where I is the moment of inertia of that molecule. And for any transition J to J plus 2, we will have the energy difference between the transition delta E to B. Delta E is equal to B into 4J plus 6. You can see this by substituting J plus 2 to the same equation and substituting back. If for this equation energy for J is equal to J itself is Bj into J plus 1, while when it is for energy for J is equal to J plus 2, it will be Bj plus 2 into J plus 3. So when we subtract energy for J plus 2 from energy for J, you will get delta E is equal to B into 4J plus 6. So the rotational energy frequency from this can be equal to nu 0 plus or minus B 4J plus 6. And similar to the vibrational energy state, this will give you the Rayleigh lines. The plus part, plus delta nu, will give you the stroke lines, and minus delta nu will give you the anti-stroke lines. Thus, the rotational Raman spectra or the rotational hyperfine structure can also be successfully explained using the quantum theory. Now, let us see some discussion over the rotational Raman spectra because it is somewhat important. We know that the energy difference or the energy is given by Bj into J plus 1. So if the transition is happening from J is equal to 0 to J is equal to 2, the answer for this, for J is equal to 0, energy will be 0. For J is equal to 2, energy will be B2 into 3, that will be equal to, energy will be equal to 6B. Therefore, you will find that delta E is equal to 6B. Therefore, if you have the Rayleigh lines, the first transition which is occurring for Rayleigh line will be at J is equal to 0. The first transition we will find at here, and that will be at a distance of 6B from the characteristic line or the Rayleigh line. And all other transitions from here, that is from J is equal to 1 to J is equal to 3, etc. All other transition from J is equal J to J plus 2, the difference between the successive energy levels will be 4B. You can just find out by simply subtracting these energy levels, and you can find that it is equal to 4B. So what we have here is, in this picture, see, this shows the rotational energy transition, that is 0 to energy 2 and coming back from 2 to 0, and this minus stroke, this part will give you the anti-stroke lines and this part is giving you the stroke lines. And the transition can be from 1 to 3, it can be from 2 to 4, etc. And only for the transition from 0 to 1, it is separated from the characteristic line at 6B, and all other transition, and the difference between all these transitions are 4B. So what we see in the spectrum is equally spaced lines on either side of the Rayleigh line. The importance of this rotational Raman spectra is that we can find the moment of inertia and the bond length of molecule. We have seen that this B is a constant, and this B contains of 8 pi square IC, where I is the moment of inertia of a molecule. Therefore, when we find the rotational energy state from this spectrum, we can find the rotational energy difference, and hence we can find B. Therefore, we can find the moment of inertia of the molecules, and from moment of inertia we can find the bond length of the molecules. Especially we do it in diatomic or triatomic molecule, and this is obtained from the rotational Raman spectra. Also, in case of homonuclear molecules such as oxygen, nitrogen, hydrogen, you have already seen while you are studying the IR spectra that the homonuclear molecules, since they do not have a permanent dipole moment, they are rotational inactive. But in the case of rotational Raman spectra, they are active. Therefore, we can get characteristic line for homonuclear molecules using rotational Raman spectra, and this will help us identify the structure of homonuclear molecules also. And it will also help us identify how these molecules are arranged, or are they linear, or are they splitted, or why is the structure of those molecules. For example, if the molecule seems to have a center of symmetry like oxygen or carbon dioxide, then in the rotational Raman spectra, its odd lines, or the characteristic lines, its even lines are absent. That is, here you can see that all lines are present for a molecule which is non-linear, or a molecule which doesn't have a center of symmetry. Here you can see that oxygen having a center of symmetry and being linear, its even lines are absent. Thus, this Raman spectra allows us to find the structure of the molecules also. Now let us see how structure determination is done for diatomic molecules using Raman spectra. For diatomic molecules, the chemical nature of the bond is actually evident from the Raman spectra. The chemical nature of bond is evident such that it shows you how far the polarizability, the alpha, changes with the nuclear oscillations. If the polarizability alpha changes with the nuclear oscillations, we will get strong Raman lines. And the chemical bond, or the nature of the chemical bond, plays a high role in change of polarizability. In case of covalent bond, that is, we are studying the covalent molecules, this in case of covalent bond, the polarizability changes highly with respect to nuclear oscillation. Thus, it will give intense Raman lines. But in the case of electrovalent bonds, the polarizability merely changes with the nuclear oscillations, and we will get few Raman lines, or maybe no Raman lines. Also, the intensity of the Raman lines is determined by the strength of the bonds. That higher the bond strength shows the increased intensity of the characteristic frequency. We have seen that the diatomic molecules with a double bond have shown a higher frequency than the diatomic molecules with a single bond. Let us see how structure determination is done for polyatomic molecules, especially for triatomic molecules. If a molecule has a center of symmetry, the vibrations are Raman active. We have seen in the previous example of oxygen and nitrogen also, it has a center of symmetry. If it is a homonuclear molecule, these homonuclear molecules are IR inactive. While you were studying the IR spectra, you might have seen that the homonuclear molecules does not give vibrational lines or IR lines, and this is because they have a center of symmetry. But if it has a center of symmetry, the vibrations are Raman active while IR inactive. So every molecule which is IR active is Raman inactive, and which are IR inactive are Raman active. Not in case of every molecule, but most of the molecules, yes. And this rule is known as the rule of mutual exclusion. in research we use this Raman spectroscopy and IR spectroscopy hand by hand. They are contemporary to each other. That is, we can find the structure of molecules. If they have a center of symmetry, it will give you the rotational Raman spectra, and if it does not have a center of symmetry, it will give you the IR. Example, in case of carbon dioxide molecule, the rotational Raman spectra will give you the alternate lines, just like the oxygen just we have seen. It will give you the alternate lines. If it gives you the alternate lines, what does it mean? It has a center of symmetry. Also, it give you a strong band at 1389 centimeter inverse. And all this analysis tells us that a carbon dioxide is a linear molecule, and it also have a center of symmetry. That is, the atoms in a carbon dioxide molecule is arranged such as oxygen, carbon, oxygen, and this is linear and it does have a center of symmetry. Similarly, in case of N2O molecule, the Raman and IR lines occur at the same frequency. That is, this particular molecule is both Raman active and it's IR active. Therefore, the molecule is not symmetric. The molecule is linear, yes, but it is not symmetric. That is, the oxygen molecule here comes in the end, and we have the nitrogen molecules, and it doesn't have a center of symmetry. Just like that, we can find the structure of a diatomic molecule or a polyatomic molecule using the Raman spectrum. Now let us see how we can take a Raman spectrum, and this Raman spectrum is taken using a Raman spectrometer. As you have already noticed, these Raman lines are going to be very feeble. We are looking into the hyperfine structures. We are looking into the stroke lines, then zooming into it, see the rotational hyperfine structure, then again zooming into it to see the rotational vibrational interactions. So these lines we are going to get from the sample. The scattered lights which we are going to get is going to be very feeble. The most of the radiation, scattered radiation, will be the Rayleigh radiation itself, that is, of the frequency of the incident light itself. Only a small amount will be stroke and a very small amount will be anti-stroke. So the Raman spectrometer, a device which is used to detect and separate these features, have to be very sensitive. Therefore, the Raman spectrometer, the most primary components of a Raman spectrometer is an excitation source, that is, source which give you the incident radiation. The sampling apparatus. The sampling apparatus means it will contain the sample and it will collect the scattered radiation from the sample, and it will have a detector. This detector will detect the different scattered lines. The first one is an excitation source. For excitation, what we need is a monochromatic source with a moderate intensity. If the intensity is very high, it will produce fluorescence in the sample. If it is very low, the scattered lights will be very low. So we need a monochromatic source, monochromatic with single wavelength, single frequency source with a moderate intensity. Such a source is laser. So laser is highly capable because of its monochromaticity, intensity and directionality. So in a Raman spectrometer, the common lasers we use is a helium neon laser, the argon laser or the krypton laser. The next part is a sampling apparatus. So sampling apparatus is used to collect the scattered light and differentiate it so that the detector can detect it. So it must contain some sort of lenses and a mirror so that the focus lights can be focused and intensified. It should contain a monochromator grating, that is, the incoming scattered light will have different frequencies. So we have to analyze every frequency separately. So it is needed that every frequencies have to be separated into its components. The incoming light have to be separated into its components, and for this we use a grating. You might have already seen grating in your laboratory experiments. This grating is used to split lines into its components. So similarly, we use a highly sophisticated grating inside this spectrometer, and what we have here is a spectrometer or a apparatus which will analyze the incoming radiation. And the detector, moving to the detector part, it will have a photomultiplier. Photomultiplier will multiply the radiations or the incoming radiation from the grating. Then it will have a photodetector. This detector will detect each and every frequency, and it is converted into electronic signals, and it is then transferred to a computer where some softwares are used to analyze its output. Now let us see how the Raman spectrometer works. We have seen that the illumination source, excitation source, is a laser. So this laser is focused into the sample using a lens, and this lens, this sample will scatter lights, and we are expecting a high intensity relay scattered lines. Again we are expecting radiation into the stroke regions, the anti-stroke regions. So all these scattered lights are again collected using another lens, and it is given to the monochromator. So these scattered lines inside the monochromator or inside the analysis apparatus is intensified. This intensified to get better results. So it is intensified using mirrors, and it is reflected back and forth between 2 or 3 mirrors, and then it is focused into the grating. As we have said, it is very important that we should split the scattered light into its components, because the difference between the stroke line, the relay line, the anti-stroke line, also this difference between the radiations happening between the vibrational spectra, rotational Raman spectra, everything is very minute. Every difference is very minute. That for this it is very important that we split these lines into its very minute detail. So we should use a monochromator. So mono means single, chroma means color. So something which separates the colors into different colors, light into a different color, is called a monochromator. Such a monochromator is grating. So using grating, one grating, maybe 2 grating, we call it as a double monochromator, or maybe 3 gratings for high sophistication. We split the lines into its very detail, and every line is individually identified. And after this separation of components is done, these lights are directed into a detector. Inside the detector we use a photomultiplier, so that the radiation which is splitted may be of very low intensity can be intensified so that the detector can detect it. And after passing through a photomultiplier, we will pass it into a CCD detector. A CCD means a charge coupled detector. Then this CCD detector is very sensitive, extremely sensitive to light, and it is very useful to detect the weak Raman lines. That's why we use the CCD detector in a Raman spectrometer. So this CCD detector will detect every light, and the result produced from this detector is passed on to some kind of a data processing software, and the software will tell us what kind of lines were scattered from that particular sample. And this is how the Raman spectrometer will work. So today in this lecture we have seen the quantum theory of Raman effect, how successfully it has explained the Raman effect, and using quantum theory we have explained the vibrational Raman spectra and rotational Raman spectra. Then we have seen how this Raman spectroscopy is used to determine the structure of diatomic and polyatomic molecule. We have also seen the Raman spectrometer, its components and its working. By this we come to end of the Raman spectroscopy. From tomorrow we will be starting the electronic spectroscopy, and thank you.